spectrum, going beyond that, of course, to gravitational waves that we've heard about earlier today. But an important component of that is indeed the low frequency component of the electromagnetic spectrum offered by the radio waves, very nicely complementing the facilities that will be available in the other parts of the spectrum. And what the radio offers actually is a very broad view of the universe, an amazingly broad scope of science that will be addressed at radio frequencies. A few examples are indicated here. In the next slide, I'll just show you how we've captured in this 2-volume set a couple of years ago just the breadth of that science. It's a 9-kilogram, 2,000-page extravaganza of all the things that our community is interested in achieving. And it really does quite a good job of capturing that breadth of science and the excitement associated with that. Some of the biggest questions I've just indicated on the one slide here, trying to capture some of the big areas. But they range all the way from planetary formation and indeed interplanetary communication, should that be out there, to testing gravity in its most extreme forms, hopefully finding that what's proved elusive so far is a pulsar black hole binary. It's almost certain that such objects exist out there, and it's a question of just looking hard enough to find them, because they will really push very hard at understanding gravity in that very extreme regime. Looking at cosmic magnetism, how it has come to be, how it has evolved over cosmic time, and indeed probing it throughout our own galaxy and throughout the universe, essentially. Magnetic filaments as a function of distance along the line of sight. Also looking to how galaxies have evolved and continue to grow to this day, fueled by neutral hydrogen that isn't only concentrated within the cores of such objects where stars are forming now, but is still being fueled in many cases, and with enough sensitivity you see that web of material around the galaxies that can fuel them to this day. The transient radio sky, fast radio bursts are a phenomenon that's appeared a couple of years ago and is now really beginning to bear fruit. Objects that we still don't understand, apart from the fact that they're occurring around us at the rate of about 10,000 a day, and they offer great potential for probing the lines of sight to those objects by measuring directly the electron content out to these cosmological distances. And so constraining, very importantly, this otherwise invisible component of the universe around us. Looking at, indeed, how the galaxies have evolved through the radio continuum mission. This is fueled by star formation, and as we have come to understand, star formation has gone through an early peak and has a subsequent decline, very likely related to the moment when dark energy has given rise to an accelerated expansion. And thus, the fuel that once prompted that star formation at very intense rates is actually diminishing, is no longer accessible to the galaxies today as it was in the past. But bringing that into much sharper focus. There are also many areas of cosmology that will be probed. I don't have time to talk about all of them today. That's why I'm just trying to give you a glimpse in this one page of some of the main areas. But they probe the very largest scales through observations at radio frequencies that aren't sensitive to the absorption that you experience at optical wavelengths. So we can see around us and form from one location about 3 pi steradians on the sky of observations that are continuous and allow us to probe indeed what's going on very largest scales, angular and of course spatial scales as well. And then indeed probing in the only way that we've currently understood to get right back to when the first stars and galaxies formed. And I will spend a couple of slides on that topic, so I'll not go on about it now. Now, we are a large community and growing. We currently have 800 members of our science working groups, but every month that is growing by tens and hundreds. And they're organized into the set of science working groups that are indicated schematically here. These are in fact posters, each of which is 2.5 meters tall, that we've just renewed and have made use of at our recent science meeting just a couple of weeks ago. But for those in those working groups, we've provided a link where you can download these posters and make use of them for events that you might be having. But they really do a good job of capturing that breadth of science and the whole scope of exciting applications that people are waiting to address. One of those is indeed probed by pulsars. And what will be possible is, in fact, detecting the entire population down to a very low limit on its luminosity function within our own galaxy that will encompass, according to the simulations, something like 30,000 of these objects. What makes them so useful is the fact that they are precision clocks. And in fact, the most precise clocks are the millisecond pulsars, of which some 2,000 should be detected in this sample. And they offer this opportunity to really probe gravity in the strongest regimes. We hope to have at least 100 relativistic binaries. These are probing gravity, including, as I mentioned earlier, that what's proven elusive, a pulsar black hole binary. And in fact, what would be most interesting of all, of course, is to probe right down to the center of our galaxy, where the hope is that there may well be pulsars that are in orbits, close orbits, around the very nucleus of our own galaxy, which will really be very exciting. As well as probing pulsars in external galaxies beyond our own, and also the Magellanic Clouds, where a couple of pulsars have currently been detected. And this will really probe general relativity to, we hope, its breaking point. That's eluded us so far, but we keep hoping that we'll bump up against that limit where Einstein didn't get far enough. It must happen at some stage, and we all keep working to find that new physics that will lie beyond that point. We've heard already about the wonderful ways that the gravity wave phenomenon has been probed by LIGO. And in fact, as already mentioned, that forms part of a suite of facilities that will probe the entire spectrum of gravitational waves from the ground, from space with the LISA experiment, using the pulsar timing, these precision clocks distributed around the galaxy to probe this frequency of the gravitational wave spectrum that is sensitive to supermassive binary black hole mergers, so 10 to the 6th, 10 to the 7th solar mass events, and indeed very nicely complementing those other facilities in filling in that spectrum. Another area of great interest, of course, is looking back in time as far as we can. This image that the Planck Observatory provided for us is a snapshot of what the universe looked like at this 400,000 years of age. And what we hope to do, in fact, is rather than just having a snapshot, fill in this important movie, essentially, of the first billion years. So going on from that image that we can see around us in all direction and bringing it right back to where we have the accessible universe today, the stars and galaxies that we see at the time when the universe has become transparent, but following it through that entire history where it was opaque to optical light, where the hydrogen was essentially providing full absorption of the UV, to the moment where reionization has gone more than halfway and then fully at this point, and then we see the universe that we know and love around us. But that important time frame in the universe's history from about 400,000 years to a billion years is what should be probed by the square kilometer array itself, by imaging in the redshifted neutral hydrogen emission line. In fact, the structures that are predicted to occur at early times will be mostly in absorption. That's where the deepest structures are predicted to have several hundred millikelvins of brightness on arc-minute sorts of scales. Whereas at the slightly later times, those intensities will be somewhat lower, some tens of millikelvin brightness on arc-minute scales. But images like this should be possible, not necessarily with the same signal-to-noise ratio. We will, at these frequencies, have some tens of millikelvin sensitivity and deep integrations. At the higher frequencies of order 1 millikelvin of sensitivity. So indeed, sort of 10 to 20 signal-to-noise in images made throughout this epoch of the universe's history. So really phenomenal, and allowing one to actually pinpoint those locations of the first ionizing sources. Where are they? Where to look? The redshift at which they occur, so that follow-up experiments can actually find those ionizing sources directly. So that's a wonderful capability that is really quite unique. And this is actually an observation, apart from, these are all 3 simulations, but this is an observation published just a year ago of the first very likely detection of a signal of this absorption feature, the global absorption feature of the cosmic dawn. Now, that hasn't been confirmed, and in fact, both the shape and the depth of this feature are surprising. So there is still quite a bit of ambiguity in the community about, is this real? And it must be confirmed. And there are, in fact, 3 or 4 experiments around the world active at this moment to try to either refute or confirm this very important observation. Previous predictions had only, in the best case, imagined something about half as deep in a more Gaussian sort of signal form. But indeed, this might be new physics that's indicated by the depth and the shape of that. But we'll have to confirm that in the coming months, we hope. Another completely different area, of course, is trying to understand where life has arisen and how common that is. What's possible at the radio frequencies is to observe many complex molecules in the interstellar medium around stars. And what would be most interesting, of course, is to look for prebiotic molecules. Glycine is one of these, with transitions that will be detectable within the regime of the frequency coverage of the square kilometer array, and allow direct searches for such prebiotic molecules in solar systems around us. So really seeing how widespread are those components of life elsewhere in our galaxy. Now, the project itself, you might ask, how did we come to choose the locations that we have? And this image of the Earth at 131 megahertz gives you the idea that where we have concentrations of people are places you actually don't really want to be with a radio observatory. And this set of spectra that covers the full frequency range of the square kilometer array gives you the same sort of impression. This one located, taken in the area of Sydney, Australia. This one in a town of Narrabri, where a current radio observatory is located. And then going out to Western Australia, the site of the low frequency component of the square kilometer array, where the population density is sufficiently low that you really get a pristine radio spectrum, at least as pristine as possible from the surface of the Earth. So the 2 sites, one of them is in the Karoo location of South Africa. It's also quite remote and radio quiet, and that's where, at this moment already, the 64 dishes of the Meerkat array are under commissioning. They will become part of the square kilometer array when that rollout achieves, when the construction is well underway. Then they will be incorporated just systematically into the square kilometer array. On the same site is another experiment at low frequencies, the Hera experiment, that's under construction, that will also probe these early phases of the universe's evolution. And in Australia, zooming in to first the country of Australia and then over onto the west, and in fact the very sparsely populated portion of Western Australia is what's called the Shire of Murchison, an area the size of the Netherlands with a population at the best of times of 110 individuals. So amazingly low population density, and therefore indeed an extremely good radio environment to work in. And on this location we also have a pathfinder on the ground. This is the ASCAP facility operated by CSIRO Astronomy and Space Science. And also on that location we have the Murchison Wide Field Array, another low-frequency experiment. And so those locations have already been taken into service, including, as indicated here, a solar power station with 1.6 megawatts of power that has got battery storage that actually provides power to that site because it is off-grid, and that does present some challenges, certainly. Now, the observatory itself is, as all the projects that we've talked about in the last couple of days, a global research infrastructure. Indicated in blue are the current members, and indeed India has been one from the get-go and has, of course, contributed very welcomely to that collaboration. And in fact, just a couple of weeks ago on the 12th of March was the signing of the final record and the signing of the convention. And there's Arun, who I hope is with us this afternoon, who represented India at that signing event. So really excellent to get that underway. It's 3 sites, but encompassing 2 telescopes and 1 headquarters location that in fact will be just 1 functioning observatory. We're now reaching the end of the design phase. That's involved an investment of some 200 million euros and 600 scientists and engineers. We hope to begin construction in 2020, and that will take about 7 years, working to a cost cap for that construction project that was established by the Square Kilometre board a couple of years ago. And then once we get that underway, we would move ahead into the design and then ultimately the construction of the phase 2 extension of the array. Now, what those sites look like, we've seen them very broadly, but in the one case covering the low frequencies will be some 130,000 antennas that individually look like this, but are organized into stations. And then indeed on the mid-site, extending that frequency coverage up to higher radio frequencies with some 215-meter diameter dishes. I'll just show you a little bit more schematically how that's built up. The individual antennas organized into these stations, 256 of them per station, and in fact 512 of such stations forming the array itself. And how it's organized on the ground is indicated within the blue outline of the current property that has been purchased for the deployment. The white locations here are where concentrations of stations are located. In choosing those station locations, we've created a good instantaneous coverage in 2 dimensions, but have obviously avoided areas that might represent some radio frequency interference risk on the one hand and terrain limitations on the other. We're zooming in now just to the very central area, and you can just see how densely it's populated. This is now at the actual scale of the individual 38-meter diameter stations and this half-kilometer region that is essentially very densely packed with the stations that provides very high brightness sensitivity to those phenomena that require it. In the case of MID, a similar sort of arrangement on the ground, but now spanning about 150 kilometers and in 3 logarithmic spiral arms. Zooming in there, we also have tight concentration at the center that again provides very high brightness sensitivity to those phenomena that require it. And in fact, just a couple of weeks ago, we had the first on-site dish prototype that was constructed with the dish being lifted onto the pedestal. So that first prototype is now in place on the ground in South Africa, which is really good news. The headquarters, as I mentioned, is located just next to the Jodrell Bank Level Telescope, 76-meter telescope, and is visible from our canteen here. And indeed, it's a lovely building that we've just taken into service from September of last year and provides the working space for the staff located at the headquarters. Now, what sets it apart is its sensitivity and survey speed. As you can see here, as a function of radio frequency, in the worst case, we're only about 10 times faster than the current state-of-the-art, but in fact, at some frequencies, that climbs to about a factor of 1,000. So an amazing improvement in survey speed, and in fact, covering the frequency range between 50 and in fact having the capability to extend right up to the frequencies covered by the ALMA observatory at high frequencies. Excellent performance of the dishes that provides that opportunity for extension to high frequencies. And what also sets it apart is the imaging fidelity. What you see here is a noiseless simulation of a snapshot image. So with the square kilometer array on the left here, and with the current best facility at these frequencies, the LOFAR array on the right. And you can just see very dramatically just that improvement in imaging performance in these dirty images. What's normally done, of course, is to undergo deconvolution, and that makes them, of course, look a lot better, but at the cost of image fidelity, because you're extrapolating information where it wasn't directly measured, where in this case it's being measured directly, instantaneously, in fact. So that's really good. The operational model for the facility, as I said, involves the headquarters, and the 2 telescope sites. And in fact, what we're really dealing with is a big data problem, starting with data rates from the individual antennas that are up into the petabits per second. After the first stage of beam formation gets down to only 7 terabits a second, comparable to what we're seeing from the dishes here. And then only subsequently to correlation, and then finally producing the data products that we are able to deal with 100 gigabits per second from each of the site in terms of the final data products that are then distributed to the regional centers where the users would interact with that data. So that allows for something manageable, but manageable only with the use of dedicated fiber links that are in service and are already being explored for making use of in our operational phase at this time. But to put it in perspective, what we are talking about is rather big on the scale of current big data users. So we're talking about the yearly, well, this is from one of the 2 telescope components. Each of them produces something like 300 petabytes a year, and that really just corresponds to much of the other kinds of things that social media make use of on that same sort of yearly timescale. So we are challenged in that regard. But indeed, with the community, particularly here in India, taking part and helping us, we will be hopeful of achieving that. This is the timeline to close with. We're now involved in having major science meetings and workshops around the key science projects that would be undertaken, involving our community in data challenges that exercise their capability for science extraction from simulated data products. Once we get telescopes in the field, the scientific commissioning will get underway. When it becomes practical to do so, we'll invite science verification experiment ideas from the community that will allow for early science to be undertaken. Once the commissioning has resulted in some stable operating modes, then we'll be inviting shared risk and then PI, and then finally the big survey proposals to get underway. But they will have involvement from early on. The key science projects teams will be involved in the commissioning throughout so that they get a taste of the data and can exercise their pipelines as soon as that becomes practical. So I hope to have all of you in the room today, as well as all of the school children that are hopefully being excited by the things that we're doing and will have a chance to take part in making use of this facility. Thanks very much for your attention.
Thank you, Robert, for updating us about the current status of the SKA project and sharing some of the scientific potential of this. Yeah.